Right. So what we'll be looking at over the next couple of lectures is what's called the disjoint paths problem. Okay. So in this problem, what you are given is a graph G. It's it's a graph, and some initial vertices and some terminal vertices. Okay, and the problem is to find disjoint paths between these vertex pairs. Okay, now the graph might be directed, it might be undirected, it might be in from a certain class, and that gives the problem lots of different flavors, right? So in general, for both directed and undirected graphs, this is NP complete, right? When this k is not fixed, when this k comes as part of the input. The problem is
you cannot solve it in polynomial in the size of the graph and k. That's all it you want to mean by NP, right? Because poly in n, m, and k.
What I mean is, if this is so, I'll
k will come as part of input because S1 T1 this is one pair, S2 T2 this is another.
Yes, it will come as part of the input. So when k is not fixed for both directed and undirected graphs, the problem is NP complete. So this is what the problem is formally, and this is a precise formulation of the problem. Now what we will be considering is this instance G is a planar digraph. Okay, and k is fixed. What we have is,
so for undirected graphs, which class of graphs it is polynomial time solvable?
for undirected graphs, when k is not fixed, it is NP hard, but
No, for some class
for
of undirected graphs,
for planar graphs, it is polynomial time solvable, and it is polynomial time in a very nice way. It is FPT for planar graphs. For directed planar graph, I'll draw a table which will lay out all the available results. So the thing is, the part of this problem, the areas where this is hard is when k is not fixed. Okay, when k is fixed, it is polynomial time and in a very nice way, right? So I mean, not for all classes, but for planar graphs definitely. So this is the result we'll look at, which is when k is I'll write it in. So this is the result we will be looking at. Disjoint paths when k is fixed is xp on planar digraphs. So what does planar mean here? It just means the underlying undirected graph is planar. Yeah. And this result came out in 94. SciComp. Okay. And after that, in around, there were many improvements to this. I mean, in this direction, but around 2011 there was another result which showed that this is not 2011, 2014. It showed that this is actually FPT. Okay. So all that is known. We know that it is FPT on planar digraphs.
Why do you say k fixed and XP? I mean,
Yeah, that is it's not a nice way of saying it, but I'm just saying that k is I mean it is XP. I'm just trying to emphasize that.
so what kind
Yeah.
of running time are you trying to say? F of k into poly in the size of polynomial in the size of the graph?
No,
or
it is
n
XP.
power- yeah, n power
It is
of-
n to the O of k. The running time for the algorithm we'll look at, it has running time n to the O of k. Okay. So
Now,
yeah.
Now, okay, so one thing. So
Right.
this is paper in 94, but later, at some later point of time, has there been any other papers, some f of k into n power c or something like that?
As far as I know, the first result that showed that this is FPT came out in 2014, 15, around that
So
time.
it has
For
been
for
proved
directed planar graphs.
directed, yeah. No, so it has been proved to be FPT later. Okay.
Yeah.
That's what I'm-
For undirected graphs, on general undirected graphs, it is actually FPT, but yeah, it was proved to be FPT with some triple exponential. Yeah, the parameter dependence was something like this. Okay, that was by Robertson Seymour in '94, I think. So for undirected graphs, we had this already in '94.
So non-planar, any hardness is known?
For non-planar,
Or maybe some subclass of graphs.
no, I do not know about hardness.
I mean, disjoint paths in directed graphs is still the status is open.
Yeah, as far as I know.
No, maybe in general graph it is hard.
For planar graphs, it is all this. All we'll look at is planar graphs, and on general graphs, nothing is known yet except the Robertson Seymour result. Okay, so I'll list all that out.
Directed graph, no, general planar directed graph, it is not known. Sorry, general directed graph, it is not known whether it is FPT or not.
General directed graphs, no, it is not known.
FPT or not?
No, not even
Only classical
whether or
version
not
is
it
known,
is.
known. Yeah.
Yeah. For undirected general graphs, it is known to be FPT.
Yeah, that I
Yeah. But we'll be looking at this result because it uses something related to the structure a graph has when you attach a certain kind of group to it. Okay, it's a different kind of approach, so that's why we'll look at it. And yeah, it came out in '94, right? The FPT result was like, I don't know, 10 years, 20 years after this. So first we need some definitions. What's a digraph? Okay. So a digraph I'll denote by D, and V will be the vertex set, and A will be the arc set where A is a subset of V squared. Okay. And the machinery that we will be looking at, that was, we'll only look at the case where the input graph is a digraph, but the machinery, it has been developed for something which is more general, which is called a quiver. So there are vertices, edges, and two functions. Okay, all right. I mean, I'll not. Yeah. Basically, these functions, what do they say? So a digraph is a specific kind of quiver. Okay. Quiver. So the technique we'll be using is called okay. The author says that this is not something very deep if you just look at the topology bit of it, but it helps to organize things in a very nice way, right? So a digraph is a specific kind of quiver, and the technique we have, it can be, it exists for these quivers. Okay, a quiver is basically the same as a digraph, but with multiple edges, parallel or anti-parallel, and loops. Okay, and the kind of digraphs we'll be looking at is ones with parallel edges and loops. Okay, not parallel edges, but yeah, just with loops. Yeah, but no. These digraphs will come up late. These digraphs with loops will come up much later. The input is we can assume to not have loops. Yeah.
Actually, one thing is that the loops are not really useful because
yeah, in the input, but
some preprocessing can generate some loops. That is okay.
Yeah.
But even
in the end, we'll have graphs with loops.
But those loops, I think, may not be useful. Okay, it depends on what kind of way it is constructed.
So these are the already known results. Okay. When I say k fixed, I'm just trying to emphasize that it will be an FPT kind of result. Yeah.
K is equal to 1, there is really nothing, whether just a path exists or not.
Yeah, it's just the connectivity problem. So planar, general, directed, undirected, it's all in P. For k equals 2, for graphs, for graphs, this is general graphs, this is FPT, right? Oh, yeah. No, I'll come to FPT later. Digraphs, yeah. This is P, but this is NP complete. Okay. For even k equals 2, it is NP complete on general digraphs.
Okay, then it's known that this para NP, so exactly is not.
Yeah. Okay.
Not even XP possible for general directed graphs.
For planar graphs, it is for general graphs, it is FPT. So obviously, for planar graphs also, it will be FPT.
FPT on K.
Planar digraphs, this is FPT. Yeah, number of pairs. And in general graphs, this is NP complete.
That is actually by NP complete.
So it means the same thing again. So yeah, it's NP complete over there. And for variable K, variable K, I just mean it comes as part of the input.
It's not a parameterized problem anymore in that.
Yeah.
So I guess
The most general variant.
K is fixed, it's actually polynomial, it's not empty.
By K fixed, I just mean like I want to talk about these kinds of.
So K is fixed means you are considering K as the parameter, and K is variable means you are trying to consider the classical version of the problems.
I think most people understand what I'm trying to get at.
That is what I mean. That is what is.
So
That is what I understand.
yeah, so those are the known results, and okay. Now I'm going to describe I'll give a general overview of the whole algorithm. Okay. It will be very vague, but yeah, it will become clear. So what the algorithm does is,
So which result are you going to describe?
Schrijver 94.
No, so here on this table, the diagram planar, that is what you are going
None
to
of these, because they are all FPT. I'm going to describe an XP result.
So for diagram planar, that place you are going to describe an XP algorithm, right?
Yeah, there is an FPT algorithm, but I'm going to talk about the XP algorithm. So because it's very different from the other algorithms there are.
The FPT algorithm is some meta result or something?
I really do not know, but it does not use a technique like this. Yeah. Yeah. For these FPT algorithms, they use the irrelevant vertex technique. Okay. So that both these algorithms. I don't know if the best ones use that technique, but for planar graphs, it has been shown that with the irrelevant vertex technique, this is the best you can do. This is the best parameter dependence you can get. Okay, double exponential. There's a kind of a lower bound. On planar graphs, this is the best you can do. So there's a specific construction of a planar graph in which the parameter dependence is that. So yeah.
D plus is the dual of D prime?
No, not exactly the dual, which is why I have put it in quotes. It's a dual and then some extra edges. Okay. So the algorithm gets this input, it will reduce that graph by contracting edges into a graph D prime, and then it will look at the dual. Okay, in the dual, it will, in the dual, what it will do is, if a solution exists for this D, that means a linkage exists for this D, in the dual it will find there will be a certain kind of configuration. Okay, and what it will do is, it will formulate the existence of that configuration as this feasibility problem. Okay, right, and that problem has a solution if and only if the D has a linkage in it. Okay, so this is really hazy what I said, but it will become clear later. So what is basically going to happen is, this huge graph is going to shrink into a tiny graph, and we'll basically brute force linkage finding algorithm. Okay, so we'll contract this onto a very small graph, and then say that, okay, if a linkage exists, then it must be one of these many. Okay, and that will be a small number, something like n to the O of k. That's where this xp running time comes from. Okay, this feasibility problem will be the feasibility algorithm will be run these many times, and the feasibility algorithm is polynomial. So overall, the algorithm's running time will be this. Okay, we'll contract the whole graph into a very small graph, and then look for some configurations in it. That's what's going to happen. Okay. So what we'll look at today will not even go past this. It will be mostly here and here, this feasibility part. Okay, so I'm just going to lay out the groundwork. So we'll need some group theory and some order theory. Okay, everyone knows what a group is, but maybe not what a free group is. Okay, so, and we'll also need to look at lattices. Yeah, a free group is something that is generated without any relations between the generators. That's why it's called free. Like there's no there are no restrictions on the generators. They can combine in any way they want. So that's why it's called free, right? Okay, but that will come a little bit later. First, we'll look at what a lattice is. Okay. Everyone knows what a partial order is, right? This, yeah. So now we come to a lattice. Okay. Okay, so this is the definition of a lattice. It's basically just a partial order, but with these two special functions on sets of two elements. These sets have to have two elements, exactly two elements, not less than one, not less than two, and not more than two, exactly two. Okay, for sets of exactly two elements, these two uh, things exist. Okay, and what are they? This is equal to the infimum of A and B with respect to this partial order, and this is equal to the supremum of A and B with respect to this partial order. So for any two elements in the two distinct elements in the lattice, the infimum and the supremum should exist. So that just means, basically it means that when you pick out two elements, you'll be able to find out an element that is greater than them, I mean the smallest element that is greater than them, and the largest element that is less than both of them. Okay,
and they must be unique.
Yeah, if they exist, they will be unique. Okay, in the sets, these infimum are over sets which have certain properties ensuring that the thing will be unique. Okay, but I'll not get into the details of that. It basically means this. Okay, infimum and supremum.
So in general partial order,
Roughly it means
right?
A and B are something like this in the order, and A or B is something that bounds it from above. A and B is something that bounds it from below.
Partial order, those two means those infimum or whatever the way you have said, means those are not necessarily unique, right? In general partial order, they are not necessarily unique, but in that
exist.
If it is not, what you are saying, not necessarily unique, what you are trying to say is it does not exist.
Okay, yeah, in partial order,
Yeah.
okay. So
If this quantity exists, it is one quantity. Yeah,
okay,
it's not a set.
Okay, I see. Yeah. In partial order, in general partial order, does not necessarily exist.
Yeah, so that's the difference between a general partial order and a lattice. Okay, these things need to exist. So that's what a lattice is. Two elements, not more than two, not less than two. Okay, and there is something else called a complete lattice. It is complete if the meet and the join they exist for arbitrary sets. Okay. Over here the sets have exactly two elements, and in a complete lattice, when the sets are of arbitrary but non-zero size, the meet and the join must exist. That's a complete lattice. Okay. So we've gone from partial orders to lattices. Now we'll look at something called the top and the bottom element of a lattice. This is a lattice. It might be the case that there is an element y which is greater than or equal to every element in L, and there is an element x which is greater than or equal to every element in which is less than or equal to every element in L. So basically x is a lower bound for L and y is a lower bound for an upper bound. Yeah. Now, this case might not always happen, right? Okay. I mean, these elements might not exist, but what we can do is we can always add 2 extra elements and extend the partial order and on this extended set, okay, such that this is the lower bound and that is the upper bound. So we can always perform this operation. Okay. So this kind of a lattice is called a bounded lattice. There is an upper bound and a lower bound, so it's called a bounded lattice. And this is nothing special. We're just adding 2 elements and you can extend the partial order to these 2 elements. Nothing changes, and it's not anything hard to do. So we'll do this. We'll look at a certain kind of lattice. We'll look at a certain kind of set, and we'll convert it into a bounded lattice by doing this. Okay. So we've looked at lattices, bounded lattices, top, bottom. Now we'll look at what's called a free group. Right. Right. So we have k symbols, and we have this operation which is called reduction. All right. So W is a word over S. This reduction function goes from words over S to words over S such that okay, there's a slight mistake here. We have this set of symbols. We define a separate set of symbols which is S plus, and that is S union S inverse. So S inverse just means G1 inverse, G2 inverse, and so on. Okay. I'm going to call it T, not S plus. Okay. So reduction is a function from T star to T star, which carries words to words, and it acts like this. So W is W with all
What is this star?
wait, hold on. Is it clear what T is? Huh? As of now, inverse means nothing. It's just another symbol. Okay.
Is that really an element of S?
Yeah, it is not an element of S. Not an element. It's distinct from S. So this reduction operation, basically what it will do is, if you have a word like this, G1, G2, G2 inverse, G3, it will convert it to this word, G1, G3. All right, that's all it does. It just removes all occurrences of a generator followed by its inverse, or an inverse of a generator followed by the generator. Because all that in a group, what would that give you? It would just give you the identity element, right? And when you multiply it out, so that's all that the reduction operation is doing. So it's that. Okay. Now the definition of free group. It's a subset of T star such that when you apply the reduction operation, or I'll say Fs, the reduction operation does not change the set. Okay. So it's all words, basically it's all words over T that do not have something like this or this in them. Okay. It's just that. So now, okay, I have not said what the okay. This is the group operation. You just concatenate words and then you again apply reduce to it, you'll get an element of Fs. That's the group operation. All right. So for example, you might concatenate G and G inverse, you'll get 1 and 1 will be in the set. Okay. I mean by 1 I mean the empty string. So the empty string will be 1 and so on. Yeah, so that is the free group. All right. And why is it called free? Because this is exactly what would happen if you had a bunch of generators from a group and you just multiplied them together without any relation between the generators. Usually when you look at a group with generators, what you also have is relations. In this case, you don't have any relations. So that's why it's called free. So like for the dihedral group, which is dihedral group is like the what it dihedral group on this D5 will be all rotations and reflections of this such that, I mean, the figure remains the same. Okay. So that group is given in terms of two generators R and S. Okay. And relations between generators. So r to the 5 is 1 and s squared is 1 and so on. All right. These are the generators and these are the relations. It would be a free group if the generators were just this. Okay. All right. So that's what is really meant by free. You just have generators, you don't have relations between the elements. This is this is D5, which is you take a regular polyhedron and S is basically this reflection about this line. You'll get the same thing.
Polygon actually or polyhedron?
Regular polygon.
Okay.
And rotation is just you rotate, you'll get this.
Of all group symmetries or something like that you want to mean?
The group of all symmetries of the pentagon. Regular pentagon. So that is D5, but it has relations. It would be a free group if those relations did not.
Yeah, so how many are possible for that?
I think like 120 or something.
Not necessarily.
120, 60.
No, all 5 factorial.
No.
No, all 5 factorial is not possible from this circuit. Carry on.
No, this is, you will find this in an elementary algebra book. It's nothing very deep.
No, probably not.
We need the free group.
No, that's why I said that. Carry on.
So yeah, that's a free group, and what we'll be looking at is this. The free group comes into the picture because what you'll do is you'll assign certain elements of the group to each edge, and you can represent a path of that in the graph using an element of the group. And what we'll look at is the free group on k letters, and these because it is a free group on k distinct letters, whatever solution you get will be vertex disjoint. So roughly that is why we are getting into free groups. Okay, so by Fk I'll mean the free group on k symbols. Okay, and we'll be looking at functions of this kind. So we have a digraph, vertex set, arc set. Okay, functions from the arc set to the free group. All right, and as we go along, this is what we'll encounter. This is like some graph in which has a solution. There's a directed path in that graph from Si to Ti, and what we will have done is we will have found a path for which this function is like this. These are all GIs. Okay. So
Not the same GI.
the same GI, same GI. So that's basically why we are getting into this. We'll look at paths like this, right? All arcs on that path will be assigned the same group element, and it will be GI. If the path is from SI to TI, the element will be GI. Okay. All right. Before getting into more about these functions, need to look at a partial order on GK. Okay, so U is, this is our partial order. Okay, partial order relation. U is less than V. U and V are some elements of GK. U is less than or equal to V if and only if U is an okay. So basically, this is important. This order relation. We'll use this to form a lattice and then extend that lattice and then look at an
Prefix, no, as words.
yeah prefix. Yeah, I should write. Sorry. GK is the this should be GK. Sorry. In the paper, it is GK. GK is the free group on K symbols. Okay. Right. That is the partial order. It is reflexive, transitive, and all that. And another thing is the length, whatever length usually means. And the length of the identity is 0. Okay. So that's the partial order on GK. This, if we, so does this partial order have a bottom?
Oh yeah, epsilon is the.
Yes. Identity is the bottom. It already has a bottom. I'm going to call the extension GK again. Okay, this is really wrong, but GK with this element that is larger than everything. Okay, so what I was talking about earlier, you can make any lattice into a bounded lattice. So this is not a lattice before you add this, but after you add this in element at infinity and an upper bound, it becomes a lattice. And we will look at this lattice.
The freeness and all is preserved and all that, is it?
It will not. I don't know how to look at this as a group. Maybe if you can, you have to modify the operation somehow. So maybe any w dot infinity is infinity, something like that might work. But I'm not sure if this thing will be still a group. Okay, but we'll look at the. Look at just the lattice. We'll extend that to another lattice and then look at an algorithm on that.
GK need not be a free group at all, because
Now it might not. What happens if you multiply two infinities? It should become infinity, right? But then what is the inverse of infinity?
I'm a bit
Yeah.
vague on this. I don't understand, because we started off with a free group. We did
Yeah.
something.
Now it might not be a free group. Depending on how you extend your operation on this, you might be able to get a group, but I'm not sure. This is definitely a lattice. All the group theory we need will only happen when these functions don't have this infinity.
So
right?
with respect to that, it's still a free group.
Yeah.
We might not have to use infinity.
Yeah. We make it a lattice, and then what happens is we'll say things like, suppose the element is not infinity, then do this. Okay. So we'll only be looking at cases where inside GK, in the original GK. So if you extend GK like that, it becomes a lattice. It will have what is this? This is the longest common prefix. This was there before, but adding the infinity gave us this function, the join. So if u and w are different, can there be a common? Can there be a common element that is greater than both of them in the original GK?
If you concatenate or something,
What I'm saying is, okay, u and w are these strings. Can there be a common element that is greater than both of them? No, because these two strings can't both be prefixes of anything, because we added the infinity. So this is infinity.
incomparable.
And when they are comparable, it is either u or v. U or w. Okay, so this is our lattice. Yeah. So what have we got so far? the free group and a lattice on the free group. Okay. Now we will be looking at those functions again and a specific kind of problem on those functions. So far we have not used planarity at all. We will only use planarity in one step, which is getting from the digraph D to its dual. That will only happen if, yeah. Okay. Now we'll look at what is called okay. Okay. These are just functions. There are no conditions on them. Functions from the arc set to the free group. Okay. They are called cohomologous if, so yeah, they are called cohomologous if there is an additional function f from the vertex set to the free group such that when you look at every arc this relation holds. Okay. So basically what that will mean is this is an arc uv, all right. You have f of v here, f of u and f of v, all right. If you, so this is your phi of A and psi of A. You can get from phi of A to psi of A by multiplying with f. Yeah, so that relation holds.
What is this phi f inverse?
F inverse. F is a function from V to gk. I don't mean the inverse of the function. I mean the inverse of the group element. Okay. So this is what it means for two functions to be cohomologous. Now, suppose we have a path, okay? I'm trying to say why this, why we need, I mean, in what way is this condition useful? Okay, suppose you have this path from U to V, and have some phi of A1, phi of A2, okay, and you also have psi of so you have this path, and you look at the arcs along that path, and you look at this function. So you might you can extend this function, and given any function on the arc set, you can extend it to paths, right? How you can extend if you just multiply along the arcs, you'll get this, all right? So suppose P is a UV path, okay? P is this path, and if psi and phi are cohomologous, then this happens. Phi of P will be equal to F inverse of U multiplied by psi of P and then F of V. Okay, this is what this condition gives you. So that tilde denotes cohomology. This is in fact an equivalence relation. Okay, that is not very important, but it is important in understanding the algorithm. And it never comes up in anything we use, but what happens is the whole solution set can be divided into equivalence classes based on this cohomology. Okay, so and what we'll essentially do is enumerate all these equivalence classes. So that's cohomology. And why did we bring this in? because on functions of this kind, okay, there is a problem called, we have this theorem which we will prove in the next class. This is not the exact statement, so don't write it down. Okay, this sigma is the maximum length of the words that occur in the description of the problem. For what we look at, this length will probably be 1. This length will be 1. Okay, so you can take this as 1. So the theorem is that for a certain problem called cohomology feasibility, when you look at functions of this kind from the arc set of a graph to the free group, and in which the permissibility sets, this term will become clear when we go to the definition of this problem. These sets are hereditary, which means S is hereditary if for all words in S you take any word, you cut it down in any way, what you are left with, contiguous substrings, they are in the set. So that is called a hereditary set. Okay, so that we'll get to again in the next lecture. This will become clear, permissibility set. So this problem, in general, it is NP complete, but when these sets are hereditary and this function is from this graph to the free group, it is solvable in polynomial time. Okay, so
Need that arc set to be from planar graph for this polynomial time solution?
no.
Even for diagram, this is true.
Yes, it is true. It is true. Yeah, for the only place where we need the planarity of the digraph is when we get to the dual. So this is the theorem we'll look at in the next lecture, and this will be used to, so this will be used to find paths equivalent to paths. Okay, so this cohomology is basically saying that one path is equivalent to another. So this cohomology feasibility problem, we will construct certain instances which will mean which basically say that if this instance has a solution, then there is an equivalent path, which is kind of simple, and yeah, that's where we'll use this polynomial time algorithm. Okay, so overall what we'll do is we'll reduce the graph into a very simple graph, and then look at all possible configurations in that graph. Okay, and see if one of those configurations is good. If it is good, that means the original graph has a solution. If it is not, if none of them are good, the original graph won't have a solution. Okay, so that's the rough idea. We'll enumerate all possible configurations, and that is where the n to the O of k comes from. The number of configurations is n to the O of k in that small graph. Yeah. So yeah, basically you will get to a graph like this. Okay, you'll get to a graph like this with one vertex in the middle and lots of, yeah, everything going into this, and this will have loops, and those loops will be around. Okay, those loops will be crazy, like they will be everywhere. And where are those? This is the final graph we'll look at, and the configurations will basically be all possible. So we're just given a planar graph, right? We are not given a planar embedding. What the algorithm tries to do is it tries to figure out ways of arranging these loops in that small graph so that it is a planar embedding. Okay, I mean roughly that is what it will do. So it will look at all the arrangements of this loop, this one loop on this one vertex. So the final graph will have 2k plus 1 vertices. Okay, and lots of loops on that one vertex. So the configurations will be like the way these loops go around the terminals. Those are the configurations.
We can work it out when we do
The next time we'll look at how to solve this problem, the cohomology feasibility problem, and then we'll look at doing this, and finally we'll look at an algorithm that uses this. Yeah, yeah. So that's that. That's.
we finally get the paths also, not just an S or a no. This thing.
Yeah, you will also get a path.
It's reducible level, okay.
But it is XP.
I know that's.
Yeah.
But we'll get the paths also.
Yeah,
Straight away.
you will get a path. So yeah, that's all for today.